Good afternoon, and welcome to the 6th Symposium, the CRISE 6, on Safety and Integrity Management of Operations in Harsh Environments, coming to you jointly from St. John's, Newfoundland, and from Texas. As promised last year, when we did this in the middle of the pandemic, we are partly here in person, and I would like to, at this time, point out that we have our exits. Our exits in this building are indicated by green signs. And you'll see some to the rear of you and on to the right. And if there is an alarm and you need to exit the building, and there are no scheduled alarms for today, but if you hear an alarm, exit through the back of the building and off to the right and out through the back. There are washrooms out through this door and to the right, and there's also a gender-neutral washroom just outside the door. My name is Darlene Spracklin-Reed, and I'm a lecturer in the Faculty of Engineering and Applied Science, and I'm really pleased to be with you here again today. Faisal Khan asked me to be involved, I think, in CRISE 1, and once you're in CRISE, you can never get out. And it's such a good group to work with that every year I come back, and it's one of my favorite parts, one of my highlights of the year is to be at CRISE. And that's because it's such a wonderful team to work with, and also I've learned so much over the years from the fine presentations that I've been able to attend. At this time, we'd like to do a land acknowledgement. We respectfully acknowledge the territory in which we gather as the ancestral homelands of the Beothuk and the island of Newfoundland, Newfoundland as the ancestral homes of the Mi'kmaq and the Beothuk. We would like to recognize the Inuit of Nunatsiavut and Nunatunavut and the Innu of Nitassinan and their ancestors as the original people of Labrador. We strive for respectful relationships with all these peoples of the province, and we search for collective healing and true reconciliation and honor this beautiful land together. At this time, I would like to ask Dr. Wei Chu to come and bring some greetings.
Thank you, Darlene. My name is Wei Chiu. I'm the Associate Dean Researcher for the Faculty of Engineering. Good afternoon, everyone. On behalf of the Faculty of Engineering and Applied Science, I'd like to welcome you to the CRISE workshop. I guess everybody here is from local, right? So I don't need to brag how beautiful the weather we have today. Anyway, I have, on behalf of the faculty, welcome for those online to this workshop too. I'll just give you a little bit of introduction of the faculty in terms of our expertise in the area. Memorial is committed to leading research to help ensure safe operations in offshore and harsh environments. The Faculty of Engineering and Applied Science is the home to strong research teams in these areas, including the research chairs in ice mechanics and safety at seas, along with research centers such as the CRISE Center, the Harsh Environment Technology Center, jointly established by the Ocean Engineering Research Center and the American Bureau of Shipping. So in partnership with the province, federal government, and industry, the faculty is developing a new harsh environment research facility to complement our existing laboratories on cold and harsh ocean research. As you are the leading expert from industry and academia, the faculty is keen on working with you to develop new collaborative research opportunities relevant to the offshore and other harsh environments. I would also like to take this opportunity to remember Dr. Charles Smith, who passed away last year. Dr. Smith was an international leader in the area of structural integrity of offshore platform and pipelines for the U.S. Mineral Management Service. I knew Dr. Smith very well. I saw firsthand how dedicated he was to ocean, offshore, and Arctic engineering research. He was also a trusted mentor to myself and young researchers. When he retired in 2009, he moved to this province with his wife, Elaine, who we are honored to have with us today. While in Newfoundland, Dr. Smith continued his commitment to the field and mentorship for another 12 years through his contribution to Memorial and the community at large. We are so grateful for his many contributions and give thanks to his family, friends, and colleagues who, upon his passing, established a scholarship in his memory. Valued is $1,000, the scholarship will be awarded each fall to a full-time student in Term 3 who is enrolled in the Ocean and Naval Architecture Engineering program and meets the scholarship requirement. So I hope you find this workshop and symposium to be insightful and helpful in exchanging research findings and ideas, but also to inspire future collaborations to continue the important work to keep people safe. So I'd like to congratulations to Dr. Salim Ahmed and his team for organizing this event to discuss the important issues around safety in the offshore and other harsh environments. I wish you have a successful workshop. Thank you.
At this point, I would like to acknowledge Dr. Salim Ahmed, who is the director of CRISE. He would like to bring you greetings, but we're having some technical difficulties with the location that he's at College Station. So I will bring you regards on his behalf, as well as Dr. Faisal Khan, who I'm sure many of you know, will also send his regards. Thank you, Wei, for your opening remarks. And as Dr. Chu mentioned, the main feature of today's CRISE 6 opening event here in St. John's is the Dr. Charles Edward Smith Memorial Lecture, with technical talks from industry and academia on Dr. Smith's primary research areas of asset integrity management and corrosion control. Today's event is to honor the professional contributions of Dr. Smith towards advancing the research and industrial outreach in the fields of oil and gas engineering in Canada and the United States. He was a long-standing member of the CRISE Steering Committee, and his support and mentorship of CRISE was truly valued. So during this event, I know it's quite warm in this room, so please feel free to get up and move about. Help yourself to some coffee, tea, and water that's at the back of the room. It's a bit of an informal event. We want you to be comfortable. And I'm going to introduce our first speaker. Today we have Mr. Howard Pike, who's going to give a personal talk on the life and professional contributions of Dr. Charles Smith. Mr. Howard Pike has 35 years of experience in the oil and gas industry in Alberta and Newfoundland. He joined the Canada, Newfoundland, and Labrador Offshore Petroleum Board when it was first formed in 1986. Mr. Pike held the position of Chief Safety Officer from 2000 to 2011. He retired from the CNLOPB in 2014 as Manager of Operations with responsibility for the administration of well operation approvals, Certificate of Fitness regulations, including monitoring certifying authorities, and the regulatory equivalency process. Mr. Pike was born and raised in St. John's and has a master's degree in engineering from Memorial University, and he is a member of the CRISE Steering Committee. Welcome, Howard.
Welcome to the first Dr. Charles Edward Smith Memorial Lecture. I still find it hard to realize that Charlie is gone. It was just over a year ago that he told me about his cancer diagnosis. It was a shock. As I prepared for this talk, I spent a lot of time reflecting on our friendship, my friendship with Charlie, realizing the subtle but important impact he had on me. The two things that stand out are his dedication to research and his mastery of networking. Charlie was a pioneering structural engineer who joined the U.S. Geological Survey's Conservation Division, then the offshore regulator in the United States, around 1977, to establish the Technology Assessment and Research Program. With the thinnest of budgets, he formed partnerships that addressed the gamut of offshore safety issues. It wasn't easy, and he was often criticized for his engagement with industry, which is critical to understanding the issues. It should be understood that regulation in the U.S. has much more of a confrontational edge than it does in other jurisdictions. But it wasn't just the research itself, it was getting the information out to the wider community, and in particular, influencing regulatory policy. Some of his accomplishments include working with the Offshore Technology Research Center at Texas A&M and others. He sponsored projects that led to the successful investigation of deep water production concepts, including TLPs, SPARs, FPSOs, and semi-submersibles. These designs are now mainstays of deep water development worldwide. He organized well control projects that included the establishment of the Deepwater Well Research Facility at Louisiana State University. He established the first ever offshore earthquake measurement network in the Pacific region. The measurement system at Platform Grace in the Santa Barbara Channel successfully recorded 5 earthquakes and the structural responses at multiple locations on the platform. He conducted research that led to new hurricane design standards for offshore structures and topsides equipment. Working with colleagues at Berkeley and Stanford, conducted groundbreaking research in human and organizational factors affecting offshore safety. This is the basis of important safety cultural studies that followed. Studied pipeline risks and corrosion management for structures and pipelines. Studied decommissioning options and their comparative environmental effects. Assessed Arctic developments, options including gravel and ice islands and monopod concepts. Conducted structural reviews leading to the renovation of Omniset, the oil spill response test facility, a venue for valuable research and testing of oil spill response techniques and equipment. Participated on the organizing committees for the International Conference on Ocean, Offshore, and Arctic Engineering. Charlie was the only offshore regulatory engineer to be selected as one of the 10 finalists for the Federal Engineer of the Year Award by the National Society of Professional Engineers. Keep in mind, the US government employs more than 130,000 engineers. In 2009, the year he retired from the Mineral Management Service, he was inducted into the Offshore Energy Center's Hall of Fame in Galveston, Texas, as a technology pioneer for health, safety, and the environment. I think Charlie was truly a master of networking, as can be seen through the collaborative research projects and organization of many international workshops, bringing together top researchers from North America and Europe. True networking by the exchange of information and ideas among people with common professional and special interests. For him, the networking wasn't just the formal workshop, but in the informal social connections associated with the workshops and the projects. I first met Charlie in the fall of 1996. The International Regulators Forum, a group of offshore safety regulators, met in St. John's that year. Some of his colleagues had given him my name. That's all it took. He was eager to promote the International Workshop on Human Factors in Offshore Operations, and ever eager to add new recruits to the International Committee on Regulatory Authority, Research and Development, IRCRAD. I think he liked the acronym. It was a committee he helped found. It was near and dear to his heart, and in truth, he was the driving force behind it. The 1996 International Workshop on Human Factors in Offshore Operations focused on the need to understand and control human errors. The workshop took a broad look at how most of the human errors occur not within the span of control of the frontline operator, but is caused instead by decisions, policies, and operating procedures handed down by higher levels of the organization and affect every aspect of the offshore industry, from design and fabrication of offshore facilities to field operations, maintenance, and to management systems for improving safety and productivity. It was clear to me at the time the focus of American research was more in the area of ergonomics and European focus was organizational issues. It led to a second workshop in 2002, which essentially focused on how to build a successful human factors incident investigation program. It was memorable for a couple of reasons. It was co-sponsored by the then Mineral Management Service and the US Coast Guard. Held in New Orleans. What could go wrong? Human factors researchers let loose on Bourbon Street. Or maybe the glass is half full. What a place for human factors researchers to study human behavior, Bourbon Street. To top it off, the day before the workshop, a freighter called Brightfield lost power while traveling the Mississippi River and took out a section of the Riverwalk, narrowly missing a riverboat casino and a cruise ship. The incident shut down the Riverwalk shopping mall and the Hilton Hotel, along with the section of the boardwalk. The commandant of the Coast Guard was the keynote speaker on the first day, which only added to the drama. It created a real buzz at the workshop with all kinds of speculation. There was great debate in the New Orleans News about the lack of collision protection for the buttresses on the bridges over the Mississippi River. It was quite an introduction to Charlie. I learned in December that Charlie was a Vietnam veteran. I probably shouldn't have been surprised given his demographic and that he attended a military college. He said he thought it was a good idea at the time. It wasn't easy at that time for Vietnam veterans. The public tended to blame the participants for the war rather than the politicians that sent them there. I'm from the tail end of that era. The thought of being dragged into that war didn't sit well with me, so my perception at the time would not have been favorable to the war, and I was caught up in the public perception of the participants. But my perception has evolved as more information has come out, research resulting in revisionist history. I think it mirrors the evolution of safety practice. A lot of early safety practice tended to blame the worker, which has now evolved much more into organizational and cultural factors. I think it was through the pioneering work of Charlie and his colleagues that safety practice has evolved. It certainly led to the evolution of my perception of the Ocean Ranger disaster, from they must have known what they were doing and they did it anyway, to one of they didn't know what they were doing, they were ignorant, but more than that, arrogant as well. That is a different problem than one of willful action. My favorite quote is by Albert Einstein. Formulation of the problem is often more important than the solution. Charlie knew the questions to ask and then how to formulate the problem. He made the solution look easy with the research he initiated, an inspiration to all of us. Thank you.
Thank you, Howard. Our next speaker is going to be Mr. Anthony Semerad. He's going to be speaking to us today about corrosion in the oil and gas industry in the offshore and submerged applications in industry and user point of view. Mr. Tony Semerad is the owner, principal MMC engineer, and PeopleSoft consultant at VAWS Consulting, Inc. He spent over 50 years in the industry and has worked in metallurgy, corrosion, mitigation, and inspection. His expertise and hands-on experience include corrosion risk assessment, abandonment and mothballing of obsolete oil and gas production equipment, design and specification of corrosion monitoring systems, risk-based inspection, forensic failure analysis, and NDT techniques. Mr. Semerad previously worked with ExxonMobil in various locations around the globe, MEP, TEC, MTC, Canadian Steel Foundries, to name just a few. He has research and teaching experience from his work with the University of Toronto and numerous other universities. Welcome.
Thank you for introduction. I am consultant now. I retired 1970. What was it? 2012, sorry, when I was 67. And I probably work more now than I work with Exxon and with Mobil and ExxonMobil. Various consulting jobs, and my wife is getting mad at me. She's sitting here. That I'm supposed to be retired, and I am still working. When I traveled quite a few places with the oil and gas industry, with Mobil and ExxonMobil. One of the places where we went on assignment for 3 years and ended up 10 years was Indonesia. And it was customary that we had parties on Sunday for the people in the compound. It was about 60 houses. And we also had different activities, like I participated on runs through jungle every week, and it's one of the days, and I was getting late because we were organizing the party at home in a house. And I was going alone, and oops, wrong place. I was rushing home because I was supposed to take care of the drinks and barbecue, and suddenly this 6-year-old girl came to me and grabbed my hand and asked me, "Where are you rushing?" I said, "I have to go home." And she said, "Well, I have to tell you something." So I was listening to it, you know, the typical 6-year-old talk. I really needed to leave. And so I said, "I'm sorry, I have to go." And she said, "Please stay and listen. So I have so much to tell you about." And I stayed, came home late, and the guests were not mad because I told them what happened. So I have one sort of directive for you. Please stay because I have so much to tell. And I split my functions. Corrosion engineers, they take care of the internal corrosion and of the external corrosion. I did both, of course, but there will be so much to talk about. I concentrate only on the external corrosion. Oops, sorry. So what is the corrosion? This is sort of overview of my talk today. I will have to go through it rather quickly because I have 50 slides. So if you want to read it more carefully, I guess the speech will be distributed later on. It's a serious threat to oil and gas industry. By the way, this is a handle on one of the platforms we had. And 40% of new steel production is used to replace whatever is corroded. And that represents about 4.5% of GNP products around the world. And it's a serious concern for people who work in the offshore industry. Typical corrosion rates, as they are categorized, are below 5 MPY, so 0.1 millimeters. And high corrosion rates are more than 10 mils per year, or more than 1/4 millimeter per year. And that's mostly in the offshore industry, really high corrosion because of chlorides. And this is a basic diagram for the corrosion process. And once you understand it, it's very easy to find solution for the corrosion problems. For corrosion to occur, you need the driving force, which is the stored energy in the metal. You need electrolyte, which is the seawater. You need oxygen. And you need to have anode and cathode, and the external conductor, which is the metal itself. If you remove one of these factors, you will stop corrosion. And as everybody knows, this is very difficult to do. So the anode is the place where the damage is occurring, where the metal oxidation is occurring and metal is being dissolved. And cathode is the place where the ions are generated and electricity flows from cathode to anode. and the conductive path is the metal itself. Here are some reactions which are associated with the process, and they are important, especially the voltages which are occurring there. On the bottom, second line from the bottom is 86 volts, which is needed to stop the cathodic and anodic processes and protect the metal by cathodic protection. There are several types of corrosion: general, localized, stress-induced, and flow-induced. Flow-induced is only in the splash zone when you have a lot of wave actions, but the other three are well alive. As I mentioned, the metal store energy, and the energy starts when you have an ore, and you have to remelt it and process it, and more energy you put into the metal, the faster the metal degrades. It's sort of a life cycle, like with people. The more energy you store and more money you spend on refining the ore, the faster it corrodes. The fastest corroding metal is lithium, which everybody probably knows by now, which is for the batteries. That's the fastest corrosion metal. Gold doesn't corrode at all. That's the least, that's on the bottom of the noble parts. Here's the table or graph of electromotive series, and you can see these various metals aligned in the table compared to the hydrogen electrode, which is considered zero. And on the left side, they are the metals which corrode the least. On the right side are the metals which corrode the most. And if you put dollar sign on each metal, you would see that as you go up there, the metals on the top, they cost the most to produce, and they also corrode the fastest. Once when I was beginner in the corrosion engineer, somebody asked me to check this problem. If you put a nail into the wood, the current nail, which is built by cold processing from wire, it stores lots of energy, and its strength is built on cold work. If you look on the bottom section, those nails were made in the past, and they were made by forging. If you put one of these forged nails into the wood, it will be there forever, whereas the new nail will corrode within a couple of years. And that's because there is a higher energy in that new nail compared to the old nail. So how much plastic deformation and mechanical processing you put into the metal will affect how quickly the metal will corrode. Here is some example of offshore corrosion, which you can see. The two pictures on the right side, and actually the third one too, this is caused by insulation. When you have neat environment rich on chlorides, and you can see that these bolts, they don't look like bolts anymore. And they probably don't have strength they actually should have. And you don't see it because you have thermal insulation around it. And so inspection and knowing these things is very important before you get into trouble real quickly. Here are these other processes which are active in the ocean. And as you can see, there's quite a few of them, and you have to be aware of all of them and take care that you are checking them. Here's a diagram. I have to have a little bit of water. This diagram shows corrosion profile on the piling. And you can see that the section which is in the ground, which is the bottom section, corrosion is very little because there is no oxygen, and also there are elements which are buffering corrosion. As you go from the bottom, from the mud line to the surface, the corrosion increases. And then it goes back to low corrosion in the tidal zone. And in the splash zone, that's the corrosion highest as it can be. This is because of the complete replenishment of the environment and the wave action of the seawater. Chlorides affect stress corrosion cracking. If you have chlorides in the water, or if you have pockets of water which have high chlorides, you can reach conditions where you have stress corrosion cracking, which is in the middle of these balloons. You can differentiate between chloride stress corrosion cracking, which is the top two figures, and the sulfide stress corrosion cracking. The chloride stress corrosion cracking looks like flames coming down through the metal. They always start with a pit on the surface where the chlorides are the highest and progress in sort of a tree-like fashion into the metal. Sulfide stress corrosion cracking is usually single line, also starting from the pit on the surface usually, but sometimes it can develop within the metal itself. This is caused by hydrogen, which is permeating through the metal and combining to hydrogen molecules and increasing volume and increasing the stresses and blocking dislocation and all kinds of other tricks which hydrogen does in the metal, which is not desirable. Metal is the only gas which can permeate actually metal ions, hydrogen ions, which can liberally permeate through the metal compared to the other corrosive gases. Bolts are the biggest problem in offshore production, and there are different type of bolts and different type of usage of the bolts. Here is a wellhead, and as you can see, there are several bolts which are oriented vertically and a number of bolts which are oriented horizontally. And which one do you think will be a problem? Would it be the vertical bolts or would it be the horizontal bolts? They are same material, same application, but surprisingly, the conditions on these bolts are not the same. Here's an example of a 10,000 psi wellhead, which blew up and went through 2 decks and ended up on the top deck next to the heliport because the bolts failed in chloride stress corrosion cracking. You can see the bolts on the bottom. And how did it happen? It happened because with this arrangement, if the water, splash water or the rain or the just moist air with chlorides concentrate in the bottom section of the flange and has no means of escaping, and that's where the damage occurs. And as you can see on the far right, those are the trees which sort of permeate into the metal till they reach certain length and depth, and that resides on breaking of the bolts. And it's a really serious problem which is easy to correct. One of the things is to put a washer on the bottom which has a groove in it so the water can run out from the cavity and does not stay in the cavity of the bolt. Another thing, in the middle, there are various caps which you can put on the bolts to prevent water going inside of the cavity of the flange. And lastly, on the far right, there are rings which you can wrap around the flange and prevent open spaces. The option 2 and 3, they sometimes use grease, which you fill up with grease. But the problem with these 3 options is that they cost money and they have to be inspected as well. So it's not a free ride because greases are known to run away from these things. And but at least the danger of chloride stress cracking is significantly reduced. The whole problem actually started, I was in West Africa. We had, the affiliate was producing for a number of years and never had problems with bolts. But some engineer from Gulf of Mexico realized, hey, they don't use stress corrosion cracking resistant bolts. And they should use stainless steel. So on this new facility, they supply the whole facility with these new stainless steel bolts. And those are the bolts which cracked, and that created significant problem for the whole operations everywhere in the world, that we had to change those bolts where they were used in ocean environment. And it's actually very easy to detect where the problem is. You take ultrasonic probe and you check it from the bottom and you check it from the top. And if there is a signal that there are these cracks in it, you simply replace the bolt. But in this facility, we had to change about 3,000 bolts. In Gulf of Mexico, it was something like 50,000 bolts. So people who were making bolts during that period, they were really happy. So how do you prevent corrosion on the bolts itself? There are several methods which are illustrated here. Most popular are the fluoropolymer coatings. They were really popular in the industry for some time. The only problem is during the shipment. They usually got damaged, the threads in particular, and that was the initiation for corrosion. So, and the others, zinc is absolutely no good in that application. So you still have to do some work and periodically check them if they are doing all right, which costs money. And here are typical production facilities. On the left, this is the old way, how we used to do it, standing platforms. There are some new ones built as well, but for the deep ocean, these are the floating facilities. And do you know what that boat on the right is? Which country it is? That's a new baby on the South American continent. This is actually ExxonMobil boat, and this field in there will be bigger than Saudi Arabian field. They expect that the income for the country will be more than 30 billion a year in 2030. So big boom over there, and possibly big boom over here as well in the east part. So pipelines, basically construction have rigid pipelines or flexible pipeline. The rigid pipeline, the biggest problem was always with the J section, which is at the very bottom, because of flexing of the pipe and wave action. Fatigue fractures were a problem all the time. The new methods on the very right, the flexible lines, it's relatively new technology, and we are still learning about it because there were some reported failures. I worked with the liners for pipelines in Alberta. That was at the beginning of my career, and that was a great thing at the time. But most of these plastics, gas can permeate through them, and they form bubbles between the steel and the liner, and the liner can collapse, and that's a bad thing because usually you cannot turn it back. Thank you. Here are typical risers, the old way, the hard pipelines. New riser after a couple of years, the paint is gone. And the very last on the right is a riser with polychloroprene sleeve. They are very popular and they are effective if they don't get damaged. They are made in Sweden, and we had some good success with them, but if you hit it with boat or with anything, that creates a void, and you get water behind it and they start to corrode. So again, you have to make sure that you inspect the risers. There are several coatings which are used for pipelines. The first two on the top, they are for internal lining, one in the bottom tacky also. But the others are for the external. For the insulation is the third on the top. PU foam is very popular also on the flexible lines in particular. Cement weight for pipelines is used quite a bit to weigh down the pipeline so they stay on the bottom. And the most popular coating these days are these 3-layer polypropylene and polyethylene, and with combination with concrete. I had some bad experience with these 3-layer PP and PE because when they assemble the lines, it's very difficult and critical on environmental application of these coatings that it's done right, and that's not very easily achievable in offshore environment. Here is the famous Russian pipeline, the second pipeline which was bombed recently, and you can see it when they are lowering into the ocean. They use a huge barge specially constructed for this purpose. The silver thing on the top in the center of the picture, of the first picture, is the galvanic anode which is used to protect the pipeline. The coatings they use on it are the last two, the 3-layer polypropylene polyethylene, and they also used concrete to weigh the anodes down. Each segment, which is 12 meters long, weighs about 52 tons. So there is no way that these pipelines would flow even though they have gas in it. The construction of flexible pipelines is very complex, and people are still going through the learning curve. There are some which using locking mechanisms, and there are some which don't have locking mechanism. That's on the right side. And here are some difficult types or difficult type of production. The last one is for wells which produce a lot of waxes and whatever. And so it's completely smooth. The other two are for water injection or general production. The new babies on the markets are the one on the left, which is completely non-metallic, and the one on the right, that's a super expensive material which was developed after the Deep Horizon failure in Gulf of Mexico. What they needed a piece of pipe which they could put on the well and safely conduct the gas to the surface, which they didn't have. And so this technology was developed specially for intervention and for critical situation in the deep ocean. There are some additional information in my paper down, which I will not show today, where you can learn more. This is how the typical oil field looks today. Very few rigid pipelines on it. Most of them are flexible, and most of these flexible pipes, they have only one problem. You can't really inspect them. So you need to have a method in place that after a certain period of production, you have to take them out and inspect them on the surface. You cannot run smart pigs through them most of the time because they would get stuck. And here are some methods which are used to inspect pipelines and risers below sea. On the top right, you can see the diver, which does it in the scuba equipment or whatever. You have robots which are operated from the platform. Or you have this new invention on very left bottom, I never used it myself, but what I read on it, about it so far, it's really interesting and exciting. I will talk about it in a minute. So this is the self-supporting robot for inspection of the sea equipment. They are automated most of these days. They only need current. They either go and get it from the platform or from the FPSO, and they do the work based on commands from a command center. And they can do all kinds of work which divers were required for it in the past, and they can go to 10,000 feet depth with no problem. This is that new technology. It's called CT, and it's very similar to MRI, which some of the people here probably had in the past, or CT scan. CT scans use computer tomography. The X-rays are used for the MRI, and the one which uses the CT technology is the one which uses gamma rays, which are not good for people, of course. So usually you have to do it in places where people are not working. And they can do really wonderful things. They can look from, they are on the outside of the pipeline or the riser, and they can look through everything what's in it, through the concrete layers, through the pipe, through multiple pipes. And it's a it was developed in 2014, and relatively a lot of things is written about it. I need to talk to someone who actually used it. I went through a seminar just recently, about 2 weeks ago, and they were speaking about it very highly. This is typical example what you can see. The beauty of this equipment is also that you can see the actual flow in the pipe, and you can see wax buildup or, pattern of flows. So it has also advantage for the operators. They know what's going on in the pipeline. You would not be able to run the SmartPix through this pipeline because you would have to clean it first. All these SmartPix, they need clean pipelines so they can do the work. And they are good. I had some good experience with them, and I had some real bad experience with them as well. We had one pipeline in West Africa, which was the most locked pipeline in the whole facility because that was the only connection to the shore where the oil was processed and stored. And we had some real horror stories from the pipeline loggers over a period of about 15 years. And one day, fishermen were fishing crabs and hooked up the pipeline and broke it in half. So we had to retrieve about 20 kilometers of it, and I personally inspected the whole 20 kilometers and didn't find a single pit in it, in spite of the, of the tools which were telling us the horror stories. And after that, we established one thing which the pipeliners, pipeline loggers didn't like. We have our own test specimen, with grooves, holes, and defects, artificial defects. And before the tool was used, they had to demonstrate that the tool will recognize them all. SmartPix cannot recognize cracks. The technology is very bad even today because you need to slow down the tool significantly in order to recognize the cracks. So they are good, but not perfect. This is typical train of SmartPix. There are multi-fingers, there are UT tools, there are sonic tools on it, whatever you want. But again, I never would use them, and that's our policy, or was our policy, that these tools had to demonstrate that they will work and do what they are saying they will do. And we did find some tools which did it. Another important thing is know your environment. When I returned from States, I was 10 years in States in the technical centers in Dallas and Houston. we had some problem with the paints in Nova Scotia. And so I asked, what are the corrosion rates? And nobody knew. We asked the Army, we asked the Sable Island people, and nobody knew what the corrosion rates were. So what we did, we used the coils, which are shown on the far right, and there are many samples you can use for testing. And it's very sensitive how you orient them. Whereas the coils are the best because the wind can blow through them, and so there is no effect of positioning of the samples that could affect the results. Lackway facility in Florida, they use plates which are exposed to the ocean, but again, they give you only one direction information. And we also tested candidate coatings, which you can see on the middle picture. We had these coils at several elevations on the platform, and we also had them on the shore. And on the shore, those are the yellow and blue lines on the bottom of this first picture. And it wasn't that significant. They were significantly lower than the offshore. And again, closer to the water level, the higher rates you got. Very interesting test, and I think we were the first in the region. People were coming to us to share the results with them later on. And in comparison, here is the Panama Canal corrosion rate done similarly. And you can see that the corrosion rate at 2 years were relatively comparable, but compared to us, the corrosion increase in the case of Sable Island, it was decreasing with time because as the corrosion layer grew on the samples, the corrosion slowed down. Here you see the effect of tropical environment, temperatures, and no cold air. We tested these coils for 2 years, and because they were coming down, we stopped testing it further. But these people were doing it for 18 years. So you can see that it significantly accelerates in tropical environments. How do you stop corrosion? By paints. It's very simple because what you do, you put a barrier between the metal and between the water. Don't think that coatings are very dense and they do work immediately. Coatings are like Swiss cheese. They are full holes if you take it under a microscope. They degrade with time. They are affected by UT. And eventually, you will have permeation of water below the coatings, and that's when the trouble starts. What coating to use? There is a number of coatings you can use, and here is the ISO document, which probably is the best document we have for offshore application and onshore as well, which specifies the conditions, C4, C5, and CX. The new version of this document, 2023, will have only one category, C5, and C4 will merge into one called C5. And for each category, this document, there is nine sections in this document. They will tell you what coatings are the best, but that doesn't end the problem you have, because our problems over we had in Sable Island were related to paint quality. They tested the paint according to the NORSOC standard, and it went through with no problem, laboratory testing. But what was delivered to site was completely something different. It wasn't the coating they tested, and it felt miserable. Basically, it felt when it was in transport from factories which fabricated it to Canada. So how many coatings we have? We have tons of coatings. Basically, they are barrier coatings, inhibitive, sacrificial, or combination of these. And zinc hop-dip galvanizing is still the best coating in the world. I don't know if you had chance or if you will have chance and go to the marine facility in Halifax Harbor where they do the same training for people who go offshore. That structure was built when I was there about 15 years ago before I visited. It looked like bright new, like they did it yesterday, and it was hop-dip galvanized. But it's not a solution for all because the structure they make these days are huge and you would need really huge facilities to do that. But there are other methods and paints which are recommended in the ISO document, and I also gave steps which you should follow in the slide which is not shown here, but it's available to read. I will go through some typical problem which you would think they are nothing, but they can sometimes affect the operation significantly. Pipe support. If you have plain pipe, coated pipe on the supports, because of the vibration and lateral movement due to the contraction and expansion, the coating usually fails within a very short time. And what happened there, you have a crevice and you have a significant corrosion problem. The resolution for that is system on the right side where it uses plastic, so the pipe actually doesn't contact the support itself. The even better way is that you hang the pipes on the support, so the water runs away from it. And I didn't show it here, but that's the next option. The biggest problem with new construction is that, and we change our specs, well, my past employer, the industry was very resistant to round edges on the paint. You can see all these examples that where the paint starts to fail is on the edges because you can't paint sharp edge. No way, there is no paint which will last it. There is method which is used quite extensively, and that's strapping of the edges with a layer of the paint, which only doubles the thickness of it, but it does not necessarily resolve the problem. We started with rounding up of the edges, and I had a great resistance in the shipyards in Halifax. You know, is it that it will cost too much money and it will be bad for both of us, company and the manufacturer. I said, try it, you know, and recommended some tools. The tool for rounding was so well that the person who was using it couldn't walk fast enough to keep up with the tool. And I think since then they are using it for everything. You know, there are tools available, and there are cases that the mills themselves round the edges, and what you need is minimum 2 millimeters. 5 millimeters is perfect. There's very few paints which will fail on 5 millimeter rounding. And it's the I-beams and these kind of things which are very difficult to paint to start with, you know. So if you have round edges, it's a good thing for success. Welding, very important thing in offshore. As you see on the picture on the right, the weld consists of numerous layers: heat-affected zone, mixed layer, a pure weld, a pure metal, and all these have certain energy in it. As I shown originally, all this energy mirror for the corrosion. So the weld can corrode on itself because of the different energies in the metal. And you can see on those pictures on the left, one is the transverse direction, one is longitudinal direction. On the straight weld, you can see the differences in stresses. And when you have that kind of differences in stresses, you will have significant corrosion. The proper way would be to stress relieve all the welds, weld only materials which are properly preheated, and that's expensive and sometimes not possible. And this problem with the welds was significant around 50s when they were building icebreakers for Canada. And the icebreakers basically fell apart in the area where it was welded because of preferential corrosion in the toe of the weld. That's the transition between the cap and the horizontal metal. That's where the corrosion is usually the highest. And you develop grooves, deep grooves around the weld, and if you don't have enough materials behind it, it can result in cracking. So very important to either select welding procedures which don't input too much heat, use proper welding materials, or use stress relieving and these kind of modern things. Here's an example of welds in one of the operations we had. You can see that when you have corrosion around those welds, you also generate hydrogen, of course. And under the paint, no matter how good that paint was, you will develop bubbles, and eventually the paint will fail. And you can see that it progresses from that part on. And it can look really ugly real quick. On the last picture on the right, I don't know if you can see it where you are sitting, there are grooves around the welds on both sides. What you have to do is to reweld those things again and try to do it better next time. Cathodic protection. Cathodic protection is extremely important for offshore operation, and you have basically two types. One is sacrificial, which is the one on the right, and you have impressed current. What you are trying to do is basically overpower the anodic parts on your metal and stop corrosion, because everything has potential big enough so the corrosion is stopped. On sacrificial method, it's effective, but not for very long distance, because they don't have such an output like the impressed current anodes. You can dial or whatever you want on your dial for the impressed current anodes, and the only problem is that if you dial too much, you will generate so much hydrogen, so you will run into another problem, so everything must be balanced. But those are the two principal methods. Like you see that Russian pipeline, that pipe is so well coated, the sacrificial anodes will work on it. They predicted 50-year life on that pipeline. Well, it lasted less than a year, but hopefully they will fix it. With impressed current, you can work indefinitely. Depends how much current you use. And you have to have source of current in order to operate the impressed current system, which is not available everywhere. So this is typical pros and cons on the sacrificial system. I am not going to read it. You can read it later. But they are very important in certain applications. Here are some typical examples of sacrificial anode on piles, subsea structures. And there is one picture which is wrong. I don't know if you see it. Anybody will suggest which picture is wrong? It's the picture on the bottom left. That's your home hot water heater and magnesium anode. Be careful what you put in that heater. Don't use zinc and don't use aluminum. If you put zinc in it, you will poison yourself. If you put aluminum in it, you will get a problem with your brain in a very short time. Magnesium is relatively good for people, but I still don't drink my tea from the warm water from the tap, because you don't know what it will do to you eventually. But magnesium is the only way. They sell you aluminum or zinc anodes in the stores because they don't know what you are using it for. But for water heaters, magnesium is the only way to go. Impressed current, here are these pros and cons on that system. It's very good, but it needs to be maintained, and you need to have source, and that becomes expensive. That's where the combination of coatings and cathodic protection systems come together in play. Because if you have good coatings, they will decrease the current demand on your impressed current system, and you will have smaller system and more effective system than if you have just CP. And here are some pictures of impressed current anodes. I'm not going to talk about it too much because I would get lost here, and and I am getting signs, so that's my last slide. And so if you have any questions, please ask me. If you can get that whole thing, there is about another 30 pages behind it with information which you may need or like, you know.
Do we have any questions? And if somebody online has questions, you can put them in the chat box. And we have somebody who will keep an eye on the chat box for questions. Okay, I think at this point we're going to take a very short break, and about a 3-minute stretch break. Get up and move around a little bit, and get yourself a glass of water, and we'll see you back here in 3 minutes. Thank you so much. I wanted to say I'm glad that we took your advice of your young friend in Indonesia to sit and listen. You had a lot to tell us, and your 50 years of experience in the industry certainly showed. And that end user perspective is so very important to the work that goes on in CRI, so thank you for bringing that to us today. You can get the kid. Everybody back? Okay, excuse me, everyone. We're going to get started up again if you want to take your seats. He's going to, so what grade is he?
Grade 12. Can apply for engineering now.
Our next guest speaker, I'd like to introduce you to Dr. Mike Pollan. He's going to speak to us today about research related to the evolution of Arctic offshore pipeline standards and technology. Mike has 30 years of experience as an engineer in offshore and onshore engineering, with projects completed on the east coast of Canada, in Alaska, the Canadian Arctic, Greenland, and the Gulf of Mexico, the Russian Arctic, and Sakhalin Island. He has been involved in offshore pipeline design and installation for the Sakhalin-1 project and BP's exploration Alaska North Star development, the world's first subsea Arctic production pipeline. In 2001, he was the co-recipient of the Hartz E&P Special Emeritus Award for Engineering Innovation for the BP Alaska North Star subsea pipeline. Welcome, Mike. Thank you.
And I'll come back to that BP pipeline in a bit, because some of the work that we had done with Charles certainly allowed us to proceed with the design of that pipeline, which has been operational for more than 20 years. So offshore pipelines in the Arctic, they face some unique challenges, different from a traditional subsea pipeline design. Although some of them have some challenges of their own, Nord Stream these days with sabotage and whatnot. But over the past 30 years or so, pipeline design standards, codes, regulations have evolved largely in part due to sponsorship by research organizations such as the MMS, PRNL, and RDC. And these are all organizations where Charles played a great role, certainly in the MMS, and then when he came to Newfoundland with PRNL, which is now ERINL, and then RDC. So from this work came about advancement in the state of the art, state of practice, emerging technologies that could be used for pipelines in the Arctic. And I'm going to talk a little bit about some aspects of that research that I had been involved with and able to interact with Charles with over about the past three decades. So first off, with some of the design challenges, and I'm talking specifically about offshore pipelines here. We have areas where we have permafrost. Even offshore you can have permafrost. Soil variability, that's not unique to the Arctic. A limited construction season, because wintertime is not always conducive to construction. Remote locations, harsh environments, these are all considerations that need to be taken into account. So you need to design for ice gouging, and then I'll talk a little bit about what these terms mean. thaw settlement, frost heave, strudel scour, etc. We have to think about, would we build in the summer versus the winter? Sometimes during the summer we only have 2 or 3 months in the Arctic to be able to get in and do what we need to do. And are we better off trying to go in and do something in the winter? And always we want to minimize impact on the environment during the installation and operations. So some of the key issues and challenges are listed there. Certainly, we'll talk a bit about strain and pipelines bending. And you can see here on the bottom right a pipeline bundle that's been subjected to some fairly significant bending or strains as part of a program to prove the pipelines. This pipeline bundle was actually installed in the Arctic after the BP North Star, but again, showing how the bundle could remain intact and the pipelines would not fail under some fairly significant strains that may be that they may be subject to given the Arctic conditions. And then the upper picture has to do with leak detection and attaching an external leak detection source. You think of some of these pipelines may have ice over top of them for 6, 7, 8 months or more in a year. And what if you have a small leak? So you have to be able to detect those small leaks. So those are some of the key things, the high strain and the leak detection, that were challenges as we went to install and design and install the first pipeline. So ice gouging, and sometimes known as ice scouring, it's the most unpredictable event for design. So you can have cases where an iceberg keel offshore here, or pressure ridge from packed up ice may touch down or scour or gouge the seabed. You don't want direct contact with the ice, so you need to figure out how deep to bury these to be safe. And Steve Bruno's in the office, or not in the office, in the audience, and Steve was looking at this 20 years ago, and Secor was looking at it 30 years ago when we were there, Steve, and you know, it still has had advancements, but there's still a lot of unknowns there. Upheaval buckling, you put your pipeline in, it's at a certain temperature, you heat it up, it wants to expand, it finds the path of least resistance, and it can move upwards. If it moves upwards, it's no longer buried as deep as you want it to be and could be subject to damage. Conversely, thaw settlement, if you have permafrost or ice lenses within your soil and you operate a pipeline higher than the ambient temperature, then you can have some thaw and some settlement. If you operate it below freezing, you may have some frost heave around the pipeline. So the pipeline can move in the different directions, and you need to look at the strains and the effects on the pipeline. One thing unique to the Arctic is strudel scour, and that's where you have a whirlpool effect where river water will flood the ice, it'll find a hole, and then the dense cold water will rush down. Now this is limited to a certain water depth, 2-3 meters, but then you can have a hydrodynamic pit form due to the soil movement, due to the water action, and then have an unsupported free span. So how do you predict that? How do you know where there's going to be a crack in the ice and where this might happen? You probably can't, so you have to look at what these typical events might look like and the effects on a pipeline. When we think of the pipelines, though, the ice gouging is generally what people are concerned with the most. And how the pipeline reacts depends on the pipeline properties. Certainly if you make it thicker, it may be more robust. The soil characteristics, even if you're not getting an impact between the ice and the pipe, are there loads being transmitted to the pipeline? The depth of the design ice gouge, how deep are these gouges? How often do they occur? And then how deep have you buried that pipeline below the seabed? And in general, trenching and backfilling is considered to be the most effective means of protection. And certainly you can trench and backfill fairly deep using certain technologies, but it costs money. And you want a project not only to be safe, but you want it to be economical as well, or it won't go ahead. So you have to go out and you have to collect a certain amount of data to look at what these ice gouges historically have been and try to extrapolate to the future as to what you might encounter or what the pipeline might encounter. And certainly with global warming, that makes it even harder today, because can we take what's happened over the last 20, 30 years and use that to extrapolate to the future? Probably not. So this is like a photograph of a seabed. And you can see that it's heavily gouged or scoured. Now, did these happen last year? Did they happen within the last 10 years, the last 100 years, last 1,000 years? You're only concerned with really with what's happened recently. The big lines going up and down, they're the center line of the survey track. So it's smaller lines or smaller scours that we're looking at. So these can be meters deep, they can be tens of meters wide, hundreds of meters long. So depending on the gouge, you may not be able to design for that realistically. Another side scan showing one of the gouges from Alaska. It's about 1.4 feet deep. Again, we need to look at what these gouge shapes are, what sort of indentation process may have taken place to understand how the soil moved or the soil was pushed. And 20, 30 years ago, this was less well understood than it is today. And again, the research has given us more insight into the forces, soil displacements associated with these different types of gouges. So here's some data from the Beaufort Sea. This was in the U.S. Beaufort, but what we've seen in collecting some data, this was work that we had done probably 15 years ago, but looking at data from the 70s and 80s, you could have gouges on the U.S. side that were 3 meters deep, and in Canada 5 meters deep, and that was known. They were known to have occurred in recent times, in the last several decades, and some very significant gouges, 5 to 9 meters, that it was unknown as to how old they actually were. So you have this ice keel moving, you have this gouging or plowing of the seabed. You don't only have that gouge or scour, you also have soil movement beneath the ice keel, as depicted there by the little arrows and a trenched pipeline showing some of the potential soil movements. So you have soil pushing on the pipeline will want to move, but it's buried, so there's some resistance. You can look at this from more than a purely elastic perspective. Can you bend the pipeline and plastically deform the pipeline and still be safe? So we look at, how deep do we need to bury this? What sort of forces can the pipeline take? And then look at the economics associated with that to try to ensure that we have a project that'll work. So understanding the loads and forces on that pipeline, what it might do to the pipeline, And then we can run numerical models, physical testing to ensure that we have a prudent design that's going to withstand the actual deformations and loads that it's going to be subjected to. And then over the years, there's been development with the evolution of computer modeling to understand, what a gouge might look like, what the driving forces might be to create that gouge, what the soil movements might be, what the failure mechanisms. So over the decades and the evolution of supercomputers, numerical modelings of geotechnical engineering, we've been able to use these as another tool into the design. And then taking it another step further, bringing the pipeline right into this as well. So some of the research that was carried out, and going back to some of my earliest interactions with Charles in the MMS, there was a project called PRIZE, Pressure Ridge Ice Scour Experiment, that was sponsored by, among others, the Miner MMS, Engineering Models for Ice Soil Pipe Interaction, sponsored by the MMS, and various phases of PRIZE. I think it went on for several years. And then here's one that we were doing with centrifuge testing, and certainly Charles would have attended some of these tests that we carried out, and some of the research they participated jointly with others, but they also had some of their own, I won't say proprietary, but perhaps they wanted to look at a certain aspect, and they would sponsor it independently of others, where others might not be interested. And this is small scale stuff, some centrifuge testing at the C-core here. Again, creating a gouge under model conditions, looking at what the model forces would be, the model displacements might be, looking at the sub-scour, sub-gouge deformations. This is the end of a gouging event in clay. These lines you see here would have been initially vertical, so we can go in then and measure and look at what the deformation might have been and how it attenuated with depth beneath the keel. So essentially that's what you're looking at there, the end of that event, and then we can see what the deformations would be. And then take this, and again with the development and advancement of numerical models, can we replicate in a computer what we've seen in the lab? And then out of this came a number of publications and the PRIZE engineering model, which then was used for design of Arctic pipelines and still is being advanced and built on today. Now, as I said, there was some research that the MMS sponsored on their own, and maybe because some of it was a little bit off the wall. And this one I'm pretty sure came out of, some of you will remember Jack Clark, and Jack was the head of C-core and a good friend of Charles. And Jack, I'm sure whenever Charles was in town, before he lived here, and others would always host a dinner at his house, and with a lot of wine. So I think that this project may have been born out of one of those visits. But, yeah, we're modeling ice gouges. We're trying to see what happens in the lab. But can we sort of be like a storm chaser and go chase gouges? So that's what we did. And I'm from PEI, so my idea was let's go to PEI and take one of the big blue garbage cans and drag it on shore and measure the gouges. But it ended up going to the Bay of Fundy and to the mud flats and putting in instrumentation, very simple instrumentation. And then every tidal change in the Bay of Fundy, these chunks of ice would float in and float out. So you would hope that one of these pieces of ice would run over your instrumentation. And I mean, we were up to our knees in mud, and there was no cell phones back then. We had to go rent a cell phone in case we both got stuck in the mud. This is Don Cameron. And you can see there on the right, you know, one of the long striations or gouges that came about. And you know, we'd go and say, okay, it ran over one of our tubes or whatever we had placed in there, and we'd go excavate it and try to measure stuff, but it wasn't highly successful. But again, it was, you know, just, you know, brainstorming around, and Charles saying, well, why don't we try this, and doing a bit of storm chasing, which was great fun. But so then applying the research. So we have this evolution of information and data. How do we use it then? And again, looking at the prize engineering model and some of the other work that came out of this, you know, what would the forces and loads be on that pipeline? And as we went and were designing the world's first offshore oil production platform for Alaska, this was Intech Engineering in Houston. And just to back up a little bit, and Lane and I were talking a little bit about this before, you know, I decided that I was going to leave SECOR in '98, and I called up Charles and I said, Charles, where should I go and apply in Houston? I don't know anybody in Houston, but you know, I think I need a change. And he gave me 3 leads, and I called them all up, and I said, Charles Smith recommended I call you up, and oh, come on in and whatnot, and yeah, happy to meet with you. And I ended up going to work with Intech Engineering on this project. So I left St. John's to go to Houston to work on Arctic projects, and which I still do today. So, you know, that Charles was a great help to me there, and certainly that's just the kind of guy that he was. So we took that data, that information, applied it to the design of the pipeline. This thing was like a gun barrel. It was 10 3/4 inch pipeline with a D over T of 12. So it was pretty thick pipeline. And taking it just to failure as well, to buckle. This work was done in stress engineering, and then pressurizing it to see what happens. But it still hold pressure with a fairly significant buckle. And so we went out and this pipeline was about 10 kilometers long, 6 miles, in up to about 15 meters water depth, 40 feet roughly, but looking at doing it from the winter, working from the ice, digging a trench, putting the pipeline in the trench. This is near shore, but as you get further offshore, we were working from floating ice. So it was thickened. It was about 1 to 2 meters thick. We had equipment working on it, and dig the trench, install the pipeline, and backfill it. And you know, you think of a pipeline, and people think, oh, steel, it's rigid, it's not flexible, it won't bend. And so you can see here that you know, it is quite flexible. And just laying it in, I'm getting the signal here. So I'm going to just run through a couple of other things as I close out here. This is the most interesting part anyways, but anyways, that ended up being a very innovative project, and it won a couple of awards. My point is that, you know, the research, you know, even this went to Intech Engineering. A lot of the research was, you know, spearheaded by Charles and others to get us to the point where we could go and do that. And there's other, I'm not going to go into the slides here, but there's other things that, you know, Charles we worked with Charles on: leak detection, trenching technology. Again, when he was at PRNL, RDC, Arctic leak detection. Again, helping and guiding the advancement of the state-of-the-art state of practice. So as I said, even though this award said Intech Engineering at that point in time, you know, part of it belongs to Charles as well. So thank you.
Does your study include also external coatings, insulation, or damage prevention?
Yeah, I mean, we did some of that, and you know, I think we had the North Star pipeline we were dragging over the ice. We had a dual layer FPE, and the anode, sacrificial anode protection. And in that cold water, as I understand it, you know, they've held up pretty good. So, and there was a guy, John LaFontaine. Did you know John? So he was with a company that did the corrosion protection CP design for BP on this.
The Russian, they had some sort of insulation on their pipe, but that was for hydrates, not for freezing on the pipeline.
Yeah, yeah. Okay, thank you.
Thanks a lot, Mike. And I really appreciated your personal reflections about Dr. Smith. And I also particularly enjoyed your slides there in the Bay of Fundy. That looked like an awful lot of fun. That's why a lot of people really get into research and why they love it the way they do. Speaking of someone who loves research, I'd like to introduce you to Susan Keynes. And full disclosure, one of my very closest friends. And I'm proud to say that I've listened to a lot of talk about corrosion. Almost everything I know about corrosion I've learned from Susan over a couple of glasses of wine. So my knowledge gets a little sketchy after a while. But Susan Keynes is going to be speaking to us today about combating corrosion under insulation with COPSIS Intelligent Digital Skin System. Dr. Keynes is a researcher and a full-time instructor with the School of Ocean Technology and cross-appointed to the Faculty of Engineering and Applied Science at Memorial University. Her research interests include corrosion and asset integrity modeling of process components in marine environments. The research includes both field and laboratory experimentation and development of asset integrity models to improve safety and reducing operating costs. Dr. Keynes has a PhD from Memorial University, a master's from Purdue University, and she got her Bachelor of Engineering degree from Dalhousie University, Nova Scotia. She's worked with General Motors of Canada Limited, New Brunswick Research and Productivity Council, and the Iron Ore Company of Canada, and she is a registered member of Paganel.
And these guys are a hard act to follow. As you can see, there were no awards and all of those things in my introduction, but I am happy to be here. Partly because although I certainly didn't know Charles as well as the rest of you, he did have quite a big impact on what I'm going to talk about. When I first started, I met Charles when he was working with RDC, and I had this idea with Dr. Khan Faisal, who may or may not be listening, to look at corrosion under insulation. And one of the things, as I was doing, I'd like to do a model of this or a model of that, we realized there was no information. We had no really good information about harsh environment or being local to our environment here in Newfoundland. So I had this idea. I lived on the ocean. Why don't I set up some wrecks in my backyard and see about what I could learn from that? So Dr. Khan, being who he was, said, yeah, you're thinking way too small. Like, let's try to put in a real proposal. And luckily at that time, Charles and RDC was looking at setting up the Argentia field test site. So lucky for me, I was the test pilot for that. While that didn't work out as I wanted, it was a great opportunity for me to get introduced to Charles, but also get somebody behind kind of an idea that just I thought this might be silly, but I'm going to give it a try. And they took it and they said, no, this could be real. This could give some real good information. So it gave me that first little taste of confidence in research, because my background is industry and not corrosion, although for some reason I've always talked about corrosion and always wanted to do corrosion. So it was, again, that first little confidence boost I got in part, and a big part from Charles. And then, again, through C-Rise and working with him here, I got a little bit more friendly with him. And the more I hear about the stories that Mike and Howard have said, I really, sadly, for me, feel like I missed out. He was very generous when I talked to him, saying, you know, you could do this. I can get you a contact with this. And I honestly, I assumed it was lip service because I was a nobody, right? I was just working on my PhD and I didn't really have anything. Little did I know, and he kept saying it every time I would meet him. And I kept thinking, oh, I should, that would be so cool. I'd like to work with NASA. I'd like to do this. And I never took him up on the opportunity. So today for me, on a really selfish level, I missed out on that. But it also leads me to maybe taking the rest of you. We're gonna have a networking event after this. So, and I know there's students here. Some of them are mine. Some of them are people that I've worked with. So that's my advice to you before we even get going, is if somebody offers to make a connection, they may not all be as great as Charles, but most people are sincere and they want to make connections and they want to help you. And that's what Charles did to me. So what this research is based on, not the technology, I'm going to put that out there, this amazing technology, the SIDS coding, is not mine. I'm just part of the validation. So now I don't even know what I'm doing. Okay, here we go. All right. So luckily, again, Tony and Mike have given a really good background to why corrosion is a problem in the offshore. So I'm speeding through all this. CUI, and again, Tony touched on that. Corrosion under insulation is a problem. And one of the biggest problems with it is that you walk around the platform, it looks like this, right? Looks great, nothing going on. So that first visual casual inspection isn't there. And I stole this from somebody else. Oh, there should be another thing that pops up there, which is really, really sad because there's another picture under there that shows some heat tracing and radiography that shows all of these bright red spots all along the bottom there. So there is something going on. There's water egress. There's that potential that Tony was talking about. Those elements that you need for corrosion are all there. They're all under there, but you can't see it. And again, if you picture a platform or something like that, there's miles and miles and miles of this. So trying to find it is a huge problem. And that's where I started with that project with RDC way back in the day, was looking at that. So some of what you're going to see in the experimental plan is the corrosion under insulation side. But another one of it is this last line of defense that we've talked about, which is coatings. And that's how I always like to think about it. Every once in a while, teach a corrosion class for engineering, and we always talk about coatings, and people say, oh, you can paint it. It's a barrier. It's going to stop corrosion. And if in a perfect world, it might. And if I could paint this and sit it on a platform and have it sit there, nobody touches it, nothing happens, it might be perfect. But if you let me put the paint on, probably not. If you have to do it out in the weather, probably not. If it's a pipeline that gets walked on, probably not. That coating, again, as everybody has said before me, if there's break or there's damage or even time and UV and all of those things, you get damage. And as soon as there's a damage, that corrosion circuit can be made. And that's the problem. So, and this is not mine, and the inventor, Farzad Hashemi, I believe is online. So if we do end up having a few questions technically, he's here as well, or I can get him via text. But I am going to preface this by saying, don't ask me how it works. Even if I may know, I'm not going to tell you. I treat it as a black box system because that's their proprietary information. And it's so cool that they definitely, and again, I sound really enthusiastic, but that's because our validations are all going perfectly, way better than we could have even hoped. So I'm still impartial, but I'm very, very positive about this. So it's really a paint-based digital feeling skin. So it's a paint. It acts like a paint, does all the things to protect as you would a paint. But when it comes to damage, if it comes to pour, even, well, again, damage, time, all of those things. As most paints do, you get some sort of damage. But luckily, with this paint, it says, hey, look right here. Oh, I don't have a thingy, and I can't touch it. So right there where that red is, that is the digital twin saying, damage here, damage here, damage here. Something has happened. I'm not saying it's necessarily corrosion, but we are saying something has happened to your coating in that spot, and you need to think about it. But on top of that, luckily, even if there is coating damage, right? You have long turnarounds for, for big maintenance planning, right? So you have dry dock in a year. With this, because again, as Tony so nicely talked about, ICCP, Impressed Current Cathodic Protection, is built in to the coating. The coating itself provides the system, the SID system provides really low voltage ICCP. So even if there is damage, and even if the electrolyte's there and the connection is there, it's not going to corrode. And that is the beauty of this. It seems wrong based on everything we've said. It seems like, well, that can't be true, which is where I started. So again, it's going from having all of these people out in the world, inspecting, trying to find that needle in a haystack there, which unless you take all the insulation off, you're probably not going to find. Or heaven forbid, you actually have a leak, you have something catastrophic happen. You know now that it's there, but something bad has already happened. So instead, you're taking that monitoring into a safe place on shore where you can watch where this is happening. Again, ideally on a digital twin, which I'm going to show you in a minute, but it can also be used in an Excel spreadsheet. As long as you have everything labeled well, it's really a very simplistic measurement tool and data acquisition. So it's not expensive, it's easy to do, well, it's better to do on such big projects. All right, so this is kind of the overview of the integrated ICCP. So again, it's polymer, electronic, and digital technologies. It is cost and performance competitive with conventional CUI coatings, simple data feeds that can be live, they can be monitored. Again, so you know what's happening, even if you're not right there all the time. So again, that's the beautiful technology, and there has been, and there's other people working on different elements of it. There's an element of biofouling protection, reduction in hydrogen evolution, things like that, being done at Dalhousie and some other places. But what we're working on here, because as I talked about with the project that Charles helped with, we have some experience with field testing and laboratory testing for corrosion under insulation. And that's what phase 2 and phase 3A are. So phase 1, we looked at just comparing a typical coating, so a commercial coating, to the SIDS coating. Not even partly for mechanical properties to make sure it did all of the jobs that any coating would do, but also added better corrosion protection. So we started off with the ISO 19, you can read it up there because I get tongue-tied when I talk about numbers, 277, just one part of it, the optional vertical pipe test. So we, if you go back here, we had all of these hot plates, they go up to 500 C, so there's a whole lot of damage right at the bottom. But what we actually found is that while both of them did eventually crack, the intertherm was much higher up. So at a lower temperature, it was still cracking. The SIDS had some cracking closer to the bottom. And again, that's the super high temperature that you would never really be running most pipes at. Also, the intertherm that we used had really significant cracking. So the SIDS had hairline crackings and maybe more in number, but they never reached the substrate. So there was no corrosion. But with the Intertherm, there were actually some reached the substrate, and there were corrosion products founded under the, oh my God, okay, I gotta go fast because I gotta get to this video. Okay, so we have another test, and we did some salt fog testing, and the really big thing that you need to see here is the black one is the SIDS coating, the other one is Intertherm, obvious, right? One is much, much better than the other. Oh, this is an old one, that's why nothing's working. Okay, so we're also doing testing in the lab that's based on ASTM 189. And this is our field test site. So the CAD drawing is actually specifically from that project with Charles. But this is where we are, out in Holyrood. So the Holyrood Marine Base, which is now called the Launch, and we're going to have that new building opening this fall. We have I'm calling it the Asset Integrity Field Test Site, but right now it's this project. So you can see the racks on the edge, that's where our field samples will go. But the big piece of news, and what I have to get to, is this was started off as a pipe dream, is having a flow loop that we wanted to test this out on, and a digital twin. So it turns out we can actually have it, and we do. So this is our on-site asset integrity pipeline. So, but I have to show you this, and I hope it just starts because I don't know how to hit play. Nope. Is there any way you can hit play back there? Sorry, I had lots of animations and stuff in this. Okay, so it's not going to work, which is really, really bad because a few of you were actually there in this live demo. We were out in Holyrood. You can see the scribe on your left. So this was made while the system was running. And if this would move on, you can see Mike McGuire up in the corner. And GRI made the digital twin for us. So you would see, I'm coming out, right here is where we made the scratch. But we didn't tell anybody that's where we made it. We were outside. And then you would see this light up in red. The whole spool would light up. And then, based on a model, based on the information gathered, you would see a darker red ring show up. So within seconds, really, of the information coming in. So it would tell you where, what spool. If you only needed to know spool, that's fine. If you needed direct location, it would tell you exactly where it happened in real time. Like, most of you know how amazing that is. So really, really happy about this. There was a big party right after, because you always think these things will work, but sometimes they don't. This one did. So now we're continuing with kind of the more validation. So this, looking at statistical significance and pushing the boundaries and things like that. But the validation testing thus far has been very, very positive. Again, the results supported disruptive new technology. And again, as any of you know about paint, if this works out, this is disruptive, right? It's continuous monitoring, it's remote, it's protection, and location detection of damage all in one thing. And then, beyond CUI, which is what I care about, there's all corrosion, and corrosion happens everywhere, as you know. Again, they're looking at wind farms and boats. Buried pipelines is what I'm sort of interested in, because that's a big thing that uses ICCP already, but the location is an issue, so that's kind of where I want to head. But there's almost no end to where this could be used. So again, I'm sorry I went so long. I really thought I would be short. So thank you very much. Does anybody have any questions, or should I run out of here? All right, we're good. Thank you.
So I think you got a little taste of why I enjoy having a couple of drinks with Susan and learning all about corrosion, because she's very enthusiastic about the work that she does. I am a little disappointed, though, that she let the whole pipe dream pun just like slide by without even acknowledging that it was a pipe dream. I love it. I want to thank you for being here with us today. I want to especially thank the steering committee, and in particular Angela Doyle, who have made this event happen. Thank you so much. The presentations that you've seen today will be available on the CRISE website. CRISE 7, can't believe it's 7 already, is going to be happening here in partnership with CRISE and MKO PSC here in St. John's, beautiful St. John's, Newfoundland, in person in October of 2023. So hopefully I'll see some of you back here then. We want to extend our thanks to ACOA and the Government of Newfoundland and Labrador for their support as well. We've ordered up a beautiful sunset for the social hour, and I encourage you to stick around. There's some refreshments and a cash bar and some networking opportunities that can happen, and who knows what can come of that. So thank you so much for your time and your attention, and we'll see you at CRI 7.